Our innovation is our flywheel regenerative shock absorber to recover wasted energy in car suspension systems. Because energy demand is expected to increase 44%, sending us into ecological overshoot, we brainstormed a couple of current things people were doing to combat this. The first thing was electric vehicles. EV vehicles are a huge combatant to the climate change issue because they decrease the amount of CO2 emitted. However, what we wondered was why we did not see EV vehicles being driven around everywhere, and why we still saw many gas vehicles. Upon further research, we found that EV vehicles have a much lower mileage than conventional diesel vehicles, disincentivizing them for consumers. We asked owners of electric vehicles and people without EVs what issues they found in EVs or what prevented them from buying an EV. We found that for people who already had EVs, the biggest stress was planning a route which allowed them to stop by an adequate number of charging stations. For those who had a gas car, they did not want to make the transition to an EV vehicle because of their lower mileage and lack of charging stations near them. In addition, we found that EVs were bad for the environment because of the amount of CO2 produced when generating the electricity for the car to run. This is of course less than the impact of gas vehicles, however, this still limits their impact on the climate change crisis. Therefore, we brainstormed ways which we could extend vehicle mileage by regenerating electricity and putting it back into the car battery, increasing the mileage of the car and incentivizing consumers, while also decreasing the need for the car to be charged so often, decreasing its CO2 output. The first thing we found that people have been doing was that they have employed regenerative braking to capture electricity. How regenerative braking works is it captures the energy used to stop the car and causes it to brake and transfers that into electrical energy to charge a generator to charge the battery. Therefore, we looked at other parts of the car and noticed that the suspension system moves a lot when the vehicle is driving, allowing us to tap into that resource and be able to generate electricity. After this, we made a simple model of VexIQ pieces and tested to see what voltage we were outputting. We used a simple rack and pinion mechanism to convert the linear motion of the suspension moving up and down into rotational motion to spin the generator. During testing, we found that the energy output was limited because of the fact that the system only generated electricity on the way down, not on the way up. Therefore, we catted our novel double clutch mechanism, which generated electricity when the suspension system is compressed and when it's relieved. It uses a ratchet and pawl mechanism which is arranged in a certain way to allow for this to happen. When the system is compressed, the right pawl engages, spinning the system clockwise while the left pawl just clicks. However, when the system is released, the left pawl engages, spinning the system clockwise while the right pawl just clicks. Because of this, we're able to double the energy output, spinning the system clockwise when the system is compressed and released. The second thing we noticed was that when our shock absorbers wasn't moving, it wasn't generating electricity. We took inspiration from flywheel batteries and salad spinners and added a flywheel to continue to generate electricity even after the system was stagnant. After testing the system with no flywheel and flywheel, we found that the flywheel achieved almost double the amount of electricity than the non-flywheel system. Because our system was powered by motors, we changed the input velocity of the motors to represent the different speeds at which the car hits the bumps and also the size of the bumps as well. We can see in our first graph that when we spun both shocks at 100% power, the flywheel maintained a consistent value, while the one without a flywheel, highlighted in red, fluctuates constantly. We also see that the flywheel continues to generate electricity even after the system has stopped, evident in the fact that the flywheel line is longer. We see that the flywheel system has a higher average and lower standard deviation compared to the non-flywheel. This trend continues through the 80 and 60% inputs. However, at the end, at the 30% input, we see the trends have flipped, with the conventional system being more stable while the flywheel fluctuates. This is because there's not enough input force in order to get the huge weight of the flywheel going. What we found was that the flywheel performed much better than the conventional when they were being spun faster, as opposed to when they were being spun slower. The sweet spot is when the system was spun between 100 to 60%. After that, the no flywheel system is better. Therefore, we needed to find a way to keep it in that 100 to 60% range. Our next step was to 3D print an actual prototype which we could test further, and we catted our initial idea on Fusion 360 and began doing test prints. Naturally, some things did not work out, and we needed to print a lot of things. However, once we got everything to fit together, it seemed like it might work.
So here is the prototype of the no double clutch non-flywheel attachment. So we have a generator with a really large gear ratio and then no flywheel. see the generator in here. There's no flywheel. And so now this is the flywheel generator setup. So here we have copper coils all around a middle flywheel. This flywheel has magnetic slots in it. You can see there are 3 slots. I've only filled up 2. So these magnets can act as weights, and they can also interact with the electrons of the coils to produce alternating current. And so once you spin, you're generating electricity without affecting the generator. The generator at the bottom. So the flywheel is attached to a generator. So this is something neat.
In order to keep testing consistent and to find a way to compress and decompress the shock absorbers, we built a testing mechanism out of XIQ parts. Our system is powered by 8 motors, acting as the weight of the car moving up and down. Through testing, we were able to find ways to improve our design further, like increasing the flywheel's weight and changing the pitch of the threaded rods to increase or decrease torque. In order to conduct testing, we connected an Arduino to the system to act as a voltmeter. We then imported the data we collected to an Excel sheet, which recorded the data in real time that the system is moving. With this data, we were able to graph the energy outputs for all of the changes which we made. We found that the average voltage output for the system with the heavy flywheel was 2.106 volts. The average voltage output for the system with the lighter flywheel was 1.725 volts. And the final average voltage, which was 1.79 volts, was with the no flywheel system. This reinforced our point that the flywheel system works really well. We also saw that the flywheel needs to be heavy, or else it just slows the system down. However, something else which is important, which physical testing gave us, was actually limits to the design. These limits would definitely come up again if we were to implement this. The first thing was friction. What we found was that when we put all the parts together, the rubbing of the different moving parts created a lot of friction, decreasing the efficiency of the system. We found that we would be able to overcome this later if we added some sort of lubrication and to dampen the impact of the systems of the parts moving together. The second thing which we found is the actual amount of torque and pressure which the system needs to withstand. This is evident with the number of threaded rods which we broke during testing. Both these issues will be more apparent when actually implementing the system, which we have not done yet. Our innovation is meant to target anyone driving a car. We hope that it can boost incentive for those who do not have an EV to get an EV and improve the experience of those who already have EV cars. We hope that the final product of the system will be able to be easily integrated on an already existing car, and the whole suspension system can be easily switched out to have our RSA implemented. We have a couple of next steps which we want to start. The first is to refine our current design. Our current design has a lot of moving parts, and because of the expected barriers which we expect in the implementation phase, we want a 3D printer prototype, which we hope can prevent those issues before they even come up. If we were to win money, we would be able to buy a couple more 3D printers in order to make this process faster and allow us to test more. After this, we hope that we can start to use more structural materials, such as metal or aluminum, in order to create a structural prototype. We want to be able to integrate this reinforced RSA onto a bike for real-world testing and allow it to face accurate levels of stress. Last year, our idea was simply an idea, which had a small prototype out of XIQ pieces. However, because of some money which we got from the Canada-wide Science Fair, we were able to buy a 3D printer and create our first accurate prototype. With the money that the Ingenious Plus could give us, we could expand our idea further and create an even more refined prototype which we could test on vehicles with.